was for notes, just a few examples. This is, I understand, probably not how your notes came to you last year. It's not color-coded. This camera's not magical like me, but my intention is that I try and give you, when I give you notes, they are coded as to what chapter they would normally be found in a normal college text. This stuff we're looking at today are pre-calc ideas. And so if you're at the end of the whole math career at Devlin, instead of organizing them by set 1, set 2, and so on, go back and organize them by big ideas. It would then be a valuable resource in college. You can say, oh, that's in the derivative chapter, and go to that part of your notebook. It's optional. I don't care if you organize it like that. But for those handful of you that want to use this as a reference, Ms. Cannon's notes are awesome. I would want to use them as a reference. This is how you might do that. If you're not sure where to put her notes, then I can go through the table of contents pretty quick and just put chapter 3, chapter 4 next to that real quick. If you're interested in that, let me know and I'll do that. So these 3 ideas are the days or the lessons at hand. Here we go. This is all, the first 2 are pretty reviewing. So say you give me a little picture of a rational function that looks like this. Let's say there's an asymptote, vertically speaking, at 2, and a horizontal asymptote at 3. And the graph looks like maybe this. And like that, yeah? Okay, let's call this f(x). Now, in terms of the vertical asymptote, can it ever be crossed? It cannot, okay? It comes by virtue of a 0 in the denominator, and there is no point that would satisfy that unless you made it piecewise and defined it somehow in a kind of manipulative fashion. It could be, but for the most part, vertical asymptotes are not crossed. Crossed. In terms of analytical connections, the idea would be if we get a limit as x goes to some constant, in this case it's 2 of the function, on a vertical asymptote case, you would see that the limit as x goes to a constant, y goes to infinity. That's how you would know a vertical asymptote if you didn't have the graph to look at. If you were just doing an analytical problem and you saw as x goes to a number, the results started getting infinitely large, you'd know it would be vertical asymptote. What about this horizontal asymptote? A horizontal asymptote, we commonly refer to it as end behavior. Notice I don't refer to it as middle behavior. Okay? Now, that said, the horizontal asymptote is just a guide for the outsides. So please don't think of it as a fence that can't be crossed. That's not true. It's a guide for the outsides. It's not something that is inviolate. We can't cross over. You can see this gets crossed over, and that's not a problem. Okay? It can be crossed. We cannot say that y is, never 3. It can be, all right? The idea analytically is the limit as x goes to infinity, as x goes to infinitely large, y starts to approach some constant, all right? So it's really 2 ideas. If x goes to infinity, y goes to a constant, then that's a horizontal asymptote. But if it says x goes to a constant, y goes to infinity, that's a vertical asymptote. So you can see it's just taking turns, one going to a constant, one going to infinity. Easy enough, yes? Yeah. Right, now we'll get some pre-response or multiple choice problems on this. The AP, you'll find they have a magical talent for making simple ideas complicated to see if you can really think your way through it, but we'll see those in a minute. Next idea, the intermediate value theorem. Again, that sounds highfalutin and fancy, but it's really just if a function goes from one point to the other in a continuous fashion, it must pass through all the points in between, all the y values in between. Oui? All righty then. So let's take a look at, and you and I might do this slightly differently, but the idea is the same, so just make sure you're doing it in a thorough way. The IVT problems on a AP exam have a little different flavor than this question, which was pulled out of a college final. Prove that there must be at least one solution to x cubed plus sine of x minus 1.2 equals 10. First of all, don't get out your calculator. Second of all, think, why must that be so? Must that be so? Why must that be so? Now think about each of those individual components. What does x cubed do by itself? Correct. Yeah. Okay. Wouldn't you agree it gets infinitely negatively large and positively large? Yeah? Mm-hmm. What about sine? It oscillates, and so, but it's fairly limited, yeah? Yeah. Negative 1 to 1. And negative 1.2 obviously then is just plus some kind of crazy shit. Must it be the case that that has to have a 0? Yeah, why? Yeah.
Because x equals 0, it's negative 1.2. And then if you plug in any point above the x-axis, it's going to be above the
Okay. So so any point above the x-axis, where would that be? Now I'm not actually asking for an actual number, just something. Let's go with the extreme. I love that you're starting with 0. 0 is a nice point to work at. And do we all agree that at 0, this thing comes out to be negative 1.2? Yeah. Agree with that? Okay. How do you know that on the right-hand side it ends up positive? How do you know that? Yeah, what dominates that expression as x gets large? X cubed. So x cubed is going to kick the crap out of sine. I mean, sine's limited to negative 1 to 1. So x cubed will dominate. It'll get really large. So it's got to be positive somewhere. It's not hard to find a place where, all right? So then saying it well. Now, in terms of what I need to show, when you are showing by the IVT or any theorem, you must first meet the conditions for the use of that theorem and say they are met. Is this function, I'll let f of x equal this so I don't have to write all that stuff. Is f of x continuous?
Yes.
It is, okay? Do you automatically just say, yeah, it's continuous, blah, 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 or do you actually think about it? Think about it. Is x cubed continuous?
Yes.
Yes. Is sine continuous?
Yes.
Yes. Is the sum of two continuous functions continuous?
Yes.
Yes. Okay. F is continuous. That must be said. Otherwise, you are going to be docked points for not meeting the conditions for the theorem. Now, this again, this might be where you and I do things slightly differently, but I need to then kind of fence it in. Like, what's your name? Like, I'm going to just fenced it in with a 1 below and a 1 above. Okay? At x equals 0, f at 0 is negative 1.2. Now, you don't have to bust out the calculator. You don't have to give me the perfect number. Give me an x that you know is going to be positive. 5, okay? At x equals 5, f of 5 is maybe 125 plus sine of 5 minus 1.2. Do you see where I'm coming from? Okay, is that positive?
Yes.
Why?
Less than negative 1.
Yeah, positive or negative, I don't know what sine of 5 is, but it can't be less than anything less than negative 1. So even at its most extreme, this would be 125 minus 1 minus 1.2. That's definitely positive. You don't have to tell me what it is, just say that's positive. Right? Now the whole idea of IET is if it went from negative to positive, it must have passed through 0. This has to have equaled 0 there. It couldn't have gone from negative 1.2 continuously to positive without passing through 0. So in my work, and again, if it looks a little different than yours, that's fine. But I would identify f equals 0 between x equals 0 and x equals 5. And would somebody who used negative 10 and 10 also be on sound footing? Yeah, it wouldn't have to be 0 and 5. If you use negative 10 and 10, that's fine too. It would prove the point just as well. Now the conclusion. This really amounts to just me stating the answer to the question and citing the IVT as my justification. So something like, by IVT, there is some x, and by my reasoning, where is that x?
Between 0 and 5.
Between 0 and 5, such that, state the question, x cubed plus sine of x minus 1.2 equals 0. That's one way to organize the work, and I think an organized, well-communicated way. And if yours is a little different, I'll be happy to read that too, as long as it's mathematically sound. Are you okay? Do you have any questions? Okay, there's one of those on tonight's homework for practice. It's more of an AP style. Hopefully it'll go well. There actually might be two. All right. Now, this is oh baby. So as I said yesterday, I want to challenge you. So I want to start getting into or laying the foundation of a little bit of delta epsilon proof. All righty? All right?
Good.
Sounds good. Okay, question. This will be maddening for you, I'm sure, but that's fun. That limit is 11. Okay? How do you know? Because if you put 2 in, it comes out to be 11, right?
Yep.
But is that what a limit is? What it is at the point?
No.
No, the limit is what it approaches. And did you approach?
No.
No, you went right there, right? Why did you do that? Because it's a line, so.
So it can't have one side of limits.
Why not? Why can't it have different one-sided limits? Because it's continuous. Okay, I was hoping you'd say that. Now, what does it take for something to be continuous? The limit exists, yeah? So you're saying the limit exists because it's continuous, and it's continuous because the limit exists. Yeah, circular reason, okay? So that actually is a no-no. If I wanted you to prove the limit is 11, you would have to be able to give me a table that gets you closer and closer to 11, so that if I saw here 10.999, I'd say, oh, okay, and this is maybe 11.001, then okay, maybe I believe you. But then I could also say, yeah, no, still don't believe you. How do you know it's not 10.9994? That's between those two. Why isn't it there? Could be, right? And so then you'd say, okay, so then I'll make another column, and I'll get you to 10.9999, and you would then, on the other side, maybe get 11.0001, and then you say, see, obviously, 11. And then I could come back and say, how do you know but that between those it's not approaching 10.9993? That's between those two. Maybe it's that. Who's to say you can average? Surely. If it's curving, you cannot. All right, well, that is just ridiculous. And so at that point, you then have to prove it, theoretically, that where you basically come back with a, all right, whatever, how close do you want me to get it? And if I say 1 billion, then you can find an x that gets me within 1 billion. And if I say 1 trillion, you can get an x that gets me within 1 trillion. And eventually you say, just find me any old delta. Whatever the delta is, I can find it. All right? So that's the idea behind a proof of a limit. Let's start, and I'm going to do this in 2 days. Today we'll do it in a numerical, table-y kind of way, and tomorrow we'll do the actual proof. So check this out. If I were to ask you to show by table that this limit is 1, it's a rather famous limit. The sine of x over x is one of the most famous limits of all calculus. Would you please get out thy calculator? Are you in AP Physics, many of you?
Yes.
Alrighty. So here's a problem every year. AP Physics is usually done in degrees. AP Calc is done in radians. And so there's always this problem of, oh, my calculator is degrees. One possible solution, if you are an Inspire, is make a document for physics, a document for calculus, put 1 in degrees, 1 in radians, and then just always open that document when you're in that class. Okay, that's one possibility. Be aware that if you're in the scratch pad and you set it to radians, it often, and make that your default, it'll actually write over all your documents into radians and stuff. So it might be best to do 2 documents, but I leave that up to you. You could also do the old, at the start of class, hit sine of 30 and see what you get. And if you're in degrees, you'll get 1/2. But if you're in radians, you'll get something else. I don't know what sine of 30 radians is, but it's something funny, I'm sure. You with me?
Yeah.
All right, well, here we go then. In terms of, again, calculator skills, I want to get that function in, and sine of x over x isn't hard to retype over and over again. But let's say this was an ugly function that I wouldn't want to retype over and over again. Then I would, oops, darn it, I'm in the scratch pad. Then I would probably want to make the function sine of x over x, so I didn't have to keep retyping it, and I could just call up f, yeah? Now the graph is fine, and it tells you it's 1, blah, blah, blah. But the goal is to make a table, okay? So we're going to show the table. Go back to your scratch pad. All right, now that the function is defined, then when you go to vars, oops, that's not what I wanted to do. Poop. When you go to your vars, not second vars, you should see the function in there, yeah? All right. Now in terms of showing a table, back to this work here, let's say that we get closer and closer to 0 by going then 1 and 0.1. And that's below, dummy. Negative and negative, yeah? And 1 and 0.1. Would you evaluate those 4 values and complete the table? .8414. Is sine of x over x even or odd? Or neither? Sine of x is odd. X is odd, so together they make even. Yeah, it's actually even. So with that said, this whole time, once I get out left-hand side, it's going to be the same on the right-hand side. Are you with me? Okay. From this, you could conclude that these are approaching 1, yeah? And the answer is not necessarily. It might be 0.9983. Okay. I don't know it's going to keep heading to 1. Maybe it flattens out. Maybe it turns back down. I don't know. So you might then say, all right, forget that. Then we'll get a little closer. And so instead of these guys, I'll go a little finer. Negative 0.1, which would still be 0.998. And 0.1, which would be 0.998. But this time, instead of going from an x of 10th away, we'll go 100th away. So let's, oh no, I might have answered my own question. That's a pity. We'll see. Okay, so if you find 100th away, you get 0.9999. Yay? All right, 0.9999. Afterwards, it diverges. What was the after that? Sorry, I forgot. 8?
Yeah.
Okay, and it is the same. All right, now working towards the theoretical. Again, you might say, well, geez, any moron could tell you it's 1. You can see it's 1. For Pete's sake, it's 1. And yet, you can always come back with about a little closer. There's still a range in there. You can, no matter how much you get close to the function, there's still, I could say, nope, get closer, nope, get closer. And you have to keep coming back with closer. So, say I will believe you if the limit, I'll believe the limit is 1 if you can find a delta x. Now would you please write in the delta x? It's not a capital delta x. It's a lowercase delta x, which looks like an unfinished 8. Like that. Okay? Delta x, that you can get the function within 1/10,000. Now, that would mean then that the difference between the function and the limit is less than 0.0001. Now actually we might, in retrospect, be there. If I took right here, at this point, what is f of x minus the limit? It's 0.9998 minus what's the limit? We say it's 1. What's the difference there? 0.0002. Oh, shucks. It's not less than. So I need to get a little closer. Find me 1. I can pick up with, I know this was close, but it would be logical then to try 0.001 or 1,000, please. Okay, so I get 1, 2, 3, 4, 5, 6 9s and then an 8, yeah? Okay, so at -0.001, I get 1, 2, 3, 4, 5, 6 9s and then an 8. It is still even, so you'll 3, 4, 5, 6, 8 at 0.001, 1.9998. Okay, and so, yes, sorry.
Doesn't that one work because it's 4 9s, not 3?
Say it again.
So when we just did the subtraction and it was 0.0002, doesn't it work because it's supposed to be 4 9s, not 3? 0.9998.
Oh, and when I did this, I had 3 9s, and it should have been 4. Good call. Thank you. I'm so sorry. So this actually was wasting my time. I apologize. You're right. Thank you. So this difference should have been. Okay. Thank you. 998. That's what you guys were mumbling about over here. Okay. Keep in mind also, it doesn't matter with respect to the sign whether one minus the other. It's just on either side within 100. So this is, oops, 0.00002, and is that less than 0.0001? It is, yeah. 2 10,000ths is less than 1. Sorry, 200 thousandths is less than 1 10,000th. So that is true. So this table actually was unnecessary. I apologize. I would believe the limit is 1 if you can find a delta x that can get the function within 1,000. Now, in terms of the conclusion we could write, the limit equals 1. In terms of answering the question, if delta x, or how close you get x to 0, equals, what was the delta x that got me there? 0.01, okay? If delta x is 0.01, then the difference between the function, sine of x over x, and the limit will be less than what they wanted, which was 0.0001. Now, this takes a while to start really making sense. So you keep flailing away, and it gradually becomes clearer and clearer and more focused, okay? Do you see the idea? Do you want to try one on the homework? You have, did I put that in the back? Do you have the homework? Okay, would you go to 20, number 20, and try 20 on your own or with your math amigos, and We'll see how this goes. To show good work, I would like to see a little bit of a I guess 6-column table, X and the function, 1 in the middle, and then 2 approach values from either side. I'm going to paste this in.
So if I could just overdo like the accuracy we need, just let me know. What would be my position?
Okay, this kind of goes to picking on some of the, so couldn't you might think, couldn't I just right away say delta x is point 0.0000000000001, boom. Well, doesn't really get the point that's going to help you with the idea. So would you please show me a little bit of an approach, and it'll help you once we get to the proof, okay? So, yeah, I understand, yeah, you're right, and you're smart, but do it this way for a reason. You know what? I don't like it. I'm gonna go back. How's it going? So tell me, either above or below, what worked for you? Are you still working? Still working, plugging in numbers. Okay, I'm gonna go to 0. Did 9,
Yeah.
it did work? Okay. Oh, shoot. Oh. 1.03. Oh, thousands.
Yeah.
Okay. So that didn't work. 1.001 did work. All right, so I tried 0.999, I got nothing, or didn't quite get there. So if you try, boom, then you get negative 1.003, 1.003. What was it above? 1.001. negative 1 point, or no, probably a little less than negative 1. What is it?
Negative 0.9.
993. Okay, sounds good. All right. So, with that said, great. What is a delta x? The limit must be what? What's the limit? Negative 1. And that's because if delta x is, so what's the delta x that got me there? It got me close enough. What's the delta x in here? Delta x that worked is 1,000. Okay. Now you might actually, you could maybe 0.003 work or something like that. So it doesn't. I just go for powers of 10 by habit because it's most logical. But you might have something else. But that is enough to get me there. And by get me there, I mean if you get within that close to x, then the difference between the function and the limit will be less than what? 0.01, which is the specified closeness. This actually, in delta epsilon proof, is the epsilon. How close they wanted you to get to the limit. They wanted you to get within 100, and the delta that gets you there is 1,000. Alrighty. Just real quick look at the graph, and then I'll move on. Linear is easier than curving. If you were to look at the graph of this, if you think about how this grows steeply, if you were to try and find, and obviously my x-axis is in the wrong place, so, okay. If you were to look at graphically what's happening, wouldn't it make sense that in order to get, if you trace back, actually, I think I'm going to put the axis back so it doesn't get caught. If this is the true limit as x approaches something, the way it's curving, if you need to get this close to y, won't that need to be even closer in x when you trace back because of the nature of the curve? Whereas the square root, you might not need to get as close. So the curve makes things a little more complicated, and we'll talk about that. Linear is super duper easy. We'll also talk about that. All right. At least that's introducing or laying the groundwork for delta epsilon proof. That's all I wanted to get done. That's it. Check. How did yesterday's homework go? Okay. I am expecting you to get back to your normal brilliance. I looked at Miss Cannon's final, or her final reviews, way harder than anything we're doing. Am I right? Yeah, so come on. Let me find it. Okay, I'm gonna stop this recording.